On December 29th, SpaceX's Dragon spacecraft fired its thrusters for over 19 minutes straight, pushing the entire International Space Station to a higher orbit. This marked Dragon's fifth successful reboost during the CRS-33 mission. But here's what's truly historic. Dragon just accomplished something Russia's Progress vehicle has dominated for over 2 decades. What did Dragon do that Progress never could? And why does this single mission mean NASA no longer depends on Russian spacecraft to keep the ISS from falling? Let's dive right in. Dragon wasn't built for this. When SpaceX designed the capsule in the early 2000s, its job was straightforward: deliver cargo to the ISS and return safely to Earth. Orbital reboost belonged to Russia's Progress vehicles, which had handled that task since 1978. Nobody questioned the arrangement because it worked. But SpaceX engineers spotted an opportunity that would require solving a problem the capsule was never designed to handle. Dragon's Draco thrusters controlled the spacecraft's own movement during flight, rotating, adjusting trajectory, executing docking maneuvers. None of them pointed in the direction needed to push a 420-ton space station forward. The solution? Install 2 rear-facing Draco engines in Dragon's trunk section, aligned perfectly with the station's velocity vector. These aren't custom-built engines. SpaceX pulled the Draco thrusters from the Crew 8 mission that had already flown astronauts to orbit. Each engine produces about 400 newtons of thrust, roughly 90 pounds of force. Together they generate 800 newtons, optimized for extended burns rather than quick pulses. Progress typically executes reboosts lasting a few minutes. Dragon just fired continuously for over 19 minutes during the December 29th burn. That's not an incremental improvement, it's a fundamental operational shift. The fuel system reveals SpaceX's practical engineering philosophy. Dragon's boost kit carries 6 dedicated propellant tanks in the trunk, filled with hydrazine and nitrogen tetroxide. These hypergolic chemicals ignite on contact without needing a spark. The tanks came from 2020 abort test units, wrapped in silver insulation with a central helium pressurant tank covered in black carbon fiber. Nothing wasted, everything repurposed. What makes this setup genuinely clever is its complete independence from Dragon's main systems. The boost kit doesn't drain the capsule's flight reserves or compromise its ability to return safely to Earth. The trunk-mounted thrusters draw from their own fuel supply, pressurized by their own helium tank, controlled through existing communication lines routed through the docking mechanism. SpaceX essentially added a separate propulsion system using recycled hardware, and it delivers roughly 9 meters per second of velocity change, equal to 1.5 Progress reboosts from a single Dragon mission. The real advantage extends beyond raw performance. Progress is expendable. Every launch burns a Soyuz 2.1 rocket that's used once and discarded. Dragon flies on Falcon 9, which lands itself and flies again. The capsule itself has flown multiple missions. This fundamentally changes the economics of keeping the ISS in orbit, but the implications run much deeper than cost saving. For over 20 years, the ISS has depended on a capability controlled entirely by Russia. Progress vehicles handle approximately 80% of the station's orbital maintenance, executing the burns needed to counteract atmospheric drag. The ISS loses about 100 meters of altitude every single day, making these reboosts absolutely critical to the station's survival. When Russia announced its withdrawal from the ISS partnership by 2028, that deadline seemed manageable. Then serious damage at the Baikonur Cosmodrome launch pad delayed Progress missions, forcing NASA to confront an urgent question. Can the ISS maintain its orbit without Russian spacecraft? Dragon's CRS-33 mission is providing the answer through 6 reboosts over 5 months, covering 25 to 33% of the station's annual altitude maintenance needs. The math becomes compelling when you realize that 3 to 4 Dragon cargo missions per year could theoretically handle the entire workload. NASA already flies multiple Dragon missions annually under existing contracts. The capability for complete operational independence already exists in the current flight manifest. Russia's planned 2028 withdrawal, once viewed as a looming crisis requiring emergency solutions, now represents a manageable transition. The Baikonur delays that might have triggered desperate contingency planning just 2 years ago are absorbed within existing American commercial capacity. Dragon converted what was a critical single-point failure into a resilient system with multiple providers, especially as NASA simultaneously qualifies Northrop Grumman's Cygnus spacecraft for reboost operations. What Russia exclusively controlled for decades is becoming a standard capability of U.S. commercial cargo vehicles. This operational shift carries strategic weight, but there's another reason NASA is analyzing every second of Dragon's thruster performance. The data being collected is worth far more than the immediate altitude gained, because it's solving a problem that doesn't exist yet. When the ISS reaches end of life after 2030, it cannot simply be abandoned. At 420,000 kilograms, the station is too massive to burn up completely during uncontrolled re-entry. Debris would scatter across thousands of kilometers, potentially over populated areas. NASA awarded SpaceX an $843 million contract to develop a dedicated deorbit vehicle capable of executing multiple powerful burns to guide the station's descent into a remote ocean impact zone near Point Nemo in the South Pacific. The engineering challenge is formidable. The deorbit spacecraft must deliver sustained, reliable thrust while attached to a massive structure in its final days. Thrusters must function flawlessly after months in harsh space conditions. Propellant systems must handle complex burn sequences. Guidance systems must adapt to the station's changing mass and structural dynamics as modules are potentially jettisoned. CRS-33 is essentially a 5-month prototype test program for these exact requirements. Each reboost burn validates critical deorbit vehicle capabilities that cannot be fully replicated in ground testing. How do thrusters perform in actual microgravity, thermal cycling, and radiation exposure? How does propellant behave in tanks during weeks between burns? How accurate is guidance when pushing 420 tons of structure? The 19-minute burn on December 29th alone generated irreplaceable operational data on sustained thrust performance. The business model reveals NASA's strategic thinking. The agency pays for immediate operational capability, cargo delivery, and ISS reboost, while simultaneously funding research and development for the future deorbit mission. SpaceX gains flight heritage and engineering data that directly informs the $843 million deorbit vehicle design. When Russian progress delays create operational gaps, Dragon fills them while testing systems for a mission years in the future. The deorbit vehicle will likely use an enhanced version of Dragon's trunk-mounted propulsion system, essentially a scaled-up boost kit. The 6 burns of CRS-33 provide flight-proven foundations for that design, allowing SpaceX engineers to model propellant requirements, thruster performance over time, and optimize burn sequences with real-world data rather than theoretical projections. When Dragon completes its 6th reboost before returning to Earth in January, it will carry engineering data that charts the path toward the ISS's eventual controlled conclusion. Since Dragon's first cargo mission in 2012, the spacecraft has been visiting the ISS for over a decade, refining operations into smooth, dependable routines. That reliability created the foundation for expanded capabilities. Dragon didn't end Russia's ISS monopoly through competition or conflict. It happened through methodical engineering and quiet competence that turned an impossible retrofit into operational reality. This is what a strategic shift looks like in real time. Not dramatic announcements or political declarations, just a cargo capsule executing 6 reboosts over 5 months, quietly dismantling 2 decades of operational dependency. Dragon didn't just prove American spacecraft can maintain the ISS independently, it demonstrated that commercial vehicles can outperform government systems designed specifically for that purpose, using recycled hardware and practical engineering instead of massive budgets. The implications extend beyond the ISS. Every data point Dragon collects during these burns moves SpaceX closer to safely deorbiting the station after 2030. Every successful thruster firing validates technologies that will guide 420 tons of structure to a controlled ocean impact. NASA is essentially funding its own deorbit vehicle development while solving immediate operational problems. Exactly the kind of efficiency that commercial spaceflight promised. And SpaceX isn't stopping here. Elon Musk announced that 2026 could mark a breakthrough year for Starship, with multiple in-orbit refueling tests planned using the upcoming Starship version 3. The remarkable part? These tests will involve refueling one Starship by docking it with another, a maneuver Musk described as docking with ourselves. If Dragon's trunk-mounted thrusters can push the ISS, what can fully fueled starships accomplish when they master propellant transfer in orbit? We're watching the foundation being built for deep space operations, one methodical test at a time. If this kind of coverage interests you, hit that subscribe button for Space Update 24 hours. What do you think Dragon's success means for the future of the ISS? Drop your thoughts in the comments below. Thanks for watching, and I'll see you in the next one.